right, welcome. So today we're going to be talking about redox reactions. So by the end of this lesson, you guys should understand how elements that are being oxidized or reduced can be identified within a redox equation. So first off, we need to understand what redox reactions actually are. So redox reactions are reactions in which electrons are transferred from one element to another. So during this process, one element loses electrons and another element gains electrons. Oxidation is losing electrons, which are going to be represented by E minus, as long as we're looking at redox equations. So oxidation is the process by which one element loses electrons. Reduction, then, is when one element gains electrons. So within the same reaction, we're going to have both oxidation and reduction, which is why these are known as redox reactions. We can think about it like this using a number line. If we look at the number line and we see that the charge or oxidation number of our element is increasing and becoming more positive, it's actually being oxidized. And the reason is because when elements lose electrons, they become more positive. Electrons are negative, and losing a negative is a positive. So when elements lose electrons, they become more positive, and they're being oxidized. Reduction is whenever elements gain electrons. And when they gain electrons, it actually makes their charge more negative. And so that's where the name reduction comes from. It's the charge, aka the oxidation number, that's being reduced. What types of reactions are going to be redox reactions? Well, there's 4 types of reactions that typically involve a transfer of electrons. Usually it's going to be synthesis, decomposition, combustion, and single replacement reactions that are going to have a transfer of electrons occur during the reaction. So these are going to be the types of reactions that could be considered redox reactions. In double replacement reactions, no electrons are being transferred. All that's happening is you're taking the positive cations and you're switching them around. The electrons aren't being transferred, it's just that we're switching partners. In redox reactions, electrons are actually moving from one element to another and charges are changing, and so that's why those are considered a different category of equation. In order to do this, we have to be able to assign oxidation numbers to elements. So oxidation numbers are similar to charges. In a lot of cases, they're the same, but oxidation numbers are different from charges because they can be assigned to elements in covalent compounds as well. And you might be asking, well, how could a charge be assigned to something that's in a covalent compound? Well, remember that a lot of covalent compounds are polar covalent compounds, and so the electrons are closer to one element than the other. That makes the element that the electrons are closer to more negative in charge because it has more electrons surrounding it, and so it's still going to have a negative oxidation number. Not necessarily a charge, but a negative oxidation number. So let's talk about the rules for assigning oxidation numbers. First off, pure elements, and any element in its naturally occurring form is going to be a pure element. So iron by itself is a pure element, or you have diatomic elements like oxygen. All of those are going to carry the oxidation number of 0, so a big goose egg there. Hydrogen, when it's in a compound, so when it's bonded to another element, is going to carry a positive 1 oxidation number. Now there's an exception to this. If you have an alkali metal bonded to hydrogen, so it's just the alkali metal and hydrogen, so NaH. Hydrogen is actually going to be the negative in that compound. So that's the only time hydrogen is going to be -1, is when it's bonded to an alkali metal. Alkali metals themselves are always going to be positive. Just like their charge on the periodic table, the alkali metals oxidation number is going to be +1. And just like the alkaline earth metals on the periodic table, the oxidation number is going to be positive 2. Halogens, again, on the periodic table carry the charge of -1. However, when those halogens are part of covalent compounds with a charge, aka when they're part of a polyatomic ion, they're not going to necessarily have that same oxidation number because they're part of a covalent compound. So halogens do not have an oxidation number of -1 if they're part of a polyatomic ion. Oxygen, when it's bonded to another element, is going to carry the oxidation number of -2. An exception to that is going to be peroxides. So hydrogen peroxide and barium peroxide here, in those cases, oxygen is going to carry a -1 oxidation number. Peroxides come from the idea that there's one hydrogen per oxide, and so right here, my hydrogen and oxygen have to carry kind of similar but opposite oxidation numbers to cancel each other out. And so if hydrogen is +1, then in this case, oxygen has to be -1. So peroxides, like these two that are here, are going to have a -1, but they're pretty rare. It's important to understand that when you're assigning oxidation numbers to the elements in a compound, that the sum of all of the oxidation numbers of those elements in the neutral compound should equal 0. All of your positives and negatives should cancel out. And we talked about that. We went over that idea when we wrote the formulas for ionic compounds. However, sometimes compounds do have a charge, like polyatomic ions. And so the sum of all of the oxidation numbers of a polyatomic ion equals the charge on that polyatomic ion. And we'll look at one of those in just a minute. So here we have our first example. We have this equation here where we have sodium and copper 1 nitrate as our reactants, and copper and sodium nitrate as our products. I have an element and a compound, and it seems to me that the metals switch places, and now I have copper by itself and a new compound. So element, compound, this is going to be a single replacement reaction. We have to assign oxidation numbers to every element in this compound to see if any of them changed. So we're going to follow the rules to do that. If I look at this equation, I see that there's a couple of elements that are by themselves. And so they're going to carry the oxidation number 0. I also see that oxygen is in a compound in both cases here. And so here I have oxygen with its -2 oxidation number. I also see an alkali metal here, and that alkali metal is going to carry a +1 charge. And on both sides of this equation, I recognize a polyatomic ion. I recognize the nitrate ion on both sides of this equation. I know that the total charge on NO3, the nitrate polyatomic ion, is going to be -1. So oxygen and nitrogen together are going to add up to -1, because the sum of all oxidation numbers of a polyatomic ion equals the charge of that ion. So that means that oxygen's oxidation number plus nitrogen's equals -1. And we need to think about it this way. Oxygen had an oxidation number of -2, but there are 3 of them in the formula, which means that the net negative energy coming from the 3 oxygens is -6. We have to add something to that, and the sum has to add up to -1 at the end. So what could we put here? What could we add to -6 to end up with -1? We could add +5. And so the charge on this nitrogen right here is going to be +5. Now notice that when I label the oxidation numbers, I'm labeling each oxygen as -2. I'm not going to write -6 above oxygen because you label each one individually to see if that individual oxidation number has changed. If it has the same oxidation number on both sides, but the subscript changes, then that would change the total net negative energy, and it might look like it was oxidized or reduced when it really wasn't. So when you're labeling the oxidation numbers for the elements, make sure you do it per oxygen or per nitrogen, and not the sum of all of the oxygens together. I see that the nitrate ion is also on the product side, and since it has the same charge, that nitrogen is going to have the same oxidation number. And so the last thing is this copper right here, but we know from writing ionic compound formulas that if nitrate carries a -1 charge, then this copper has to carry a +1 charge in order to cancel that out. So then we have to take a look at the equation and figure out what elements changed. And by looking at that, we have to figure out which one was oxidized and which one was reduced. So if I look at this problem, it seems to me that 2 elements have had their oxidation numbers change. Sodium went from 0 to +1, and copper went from +1 to 0. So we need to think about it for just a second, and we can use that number line to help us. If sodium went from 0 to +1, then it moved in a more positive direction on our number line, and it was actually oxidized. So sodium was oxidized in this reaction. Copper didn't become negative, but it went from +1 down to 0, and so again, it moved in a negative direction on the number line, which means that it was reduced. So copper was reduced. What we also have to be able to do is write a reaction for the oxidation part of this chemical reaction and write an equation for the reduction part of this chemical reaction. So for oxidation, we can write the half reaction for oxidation this way. Sodium started off as a reactant with no charge, no oxidation number. It was 0. On the product side, it had an oxidation number of +1. That's a difference of 1 single space on our number line. So it moved from 0 to +1, which is just 1 jump on the number line. And so that means that it lost a single electron. To represent the electron that was lost, we're going to put an electron on the product side of this equation. And here's what this should look like. Here I have my neutral sodium, and here I have my sodium that's lost an electron, and here's the electron that's been separated from it. For the reduction part of this equation, we're going to kind of look at it the same way. Copper started off with a +1 oxidation number, and at the end of this reaction as a product, it had 0 oxidation number, so it was a neutral element. What happened was copper gained 1 electron, so it went from +1 to neutral. It moved 1 space on the number line. It gained 1 single electron. So we're going to represent that by adding an electron to the reactant side of this equation. So I have 1 electron being lost, 1 electron being gained. It's important to look at the number of electrons that are being lost and being gained and make sure that they're the same, because we still have to follow the law of conservation of matter. You can't lose 10 electrons and only have 2 end up being gained, because then we have 8 electrons disappearing somewhere, and that doesn't work. So the number of electrons being lost and gained has to be the same, and in this case it is. And that also indicates to me that this equation is already balanced. So I don't have to add any coefficients anywhere. In the next example, I see CH4, which is a hydrocarbon, and oxygen, reacting to form carbon dioxide and water. So this is a classic example of a combustion reaction. And we're going to go through here and label all of the oxidation numbers before we decide what was oxidized and what was reduced. So the easiest one is to label this oxygen right here. It's an element, a pure element, and so its oxidation number is going to be 0. Another easy thing to do is pick out all of the oxygens that are in compounds and label them with a -2, because each of those oxygens in those compounds is going to carry an oxidation number of -2. I also see hydrogen present in some compounds, and since in none of those compounds is it bonded to an alkali metal, these hydrogens are going to have oxidation numbers of +1. So really the only one we have to do any thinking about is going to be carbon. So I'll start with this one over here in carbon dioxide. I have 2 oxygens, and each oxygen in that compound carries a -2 oxidation number. That gives me a net negative charge of -4. We have to add something to that, and the charge on this compound is 0. So what are we going to add to -4 to end up with 0? We're going to add +4. So +4 is going to be the oxidation number for the carbon in carbon dioxide. On the reactant side, I see that there are 4 hydrogens, each with the oxidation number of +1. So that's 4 times +1 that's positive 4. We have to subtract, in this case, something to end up with a net overall oxidation number sum of 0. So what can we subtract from 4 to get 0? We're going to subtract 4. And since we're subtracting 4, that means that the oxidation number for this carbon is negative 4. So now we need to look back through this reaction and figure out what was oxidized and what was reduced, what changed. And so a couple of things jump out at me. I see that that carbon we just looked at went from negative 4 to positive 4. So it actually changed quite a bit, and it went from negative to positive. And so if we're moving in this direction in the number line, it's becoming more positive. That carbon was oxidized. The other element that I see change throughout the course of the reaction is oxygen. So as a reactant, it had an oxidation number of 0, but as a product, has an oxidation number of negative 2. So that means that it moved in a more negative direction on the number line. And since it's moving in the negative direction on the number line, it's being reduced. It's gaining electrons. So now we need to think about our oxidation and reduction half equations. We have to represent these changes using separate equations for oxidation and reduction. So the first thing I see is I have this carbon here. Carbon went from negative 4 as a reactant to positive 4 as a product. And if I think about that on the number line, it actually moved 1, 2, 3, 4, 5, 6, 7, 8 spaces across this number line. So if it moved 8 spaces on the number line, it actually lost 8 electrons. And I'm going to add those 8 electrons to the product side of my oxidation half reaction. It's important to note that even though those electrons are being lost, we're not subtracting them from any point in an equation. You never have subtraction in chemical equations. What happens is we have that carbon with its 4 extra electrons turn into a carbon that's missing 4 electrons, and a total of 8 electrons has been separated from that carbon. And so we just show those 8 electrons being separated on the product side from carbon. Now, oxygen is a little bit different. Oxygen is a diatomic element. So we're going to actually represent it as a diatomic element in our half reaction as well. So we have O2 as a reactant, and then even our reduction half equations have to be balanced. Now I don't have diatomic oxygen over here, I have oxygen and compounds, but I need 2 of them to balance out this half reaction. So if it's a diatomic element, represent it as a diatomic element in its reduction or oxidation half equation as well. If it's not a diatomic element, you don't have to use a 2 as a subscript. You can balance it by using a 2 as a coefficient. Now it went from an oxidation number of 0 to an oxidation number of negative 2. So it went from 0 to negative 2. So it moved 2 spaces on the number line. And if it moved 2 spaces on the number line, what happened was it gained 2 electrons. Now that's per oxygen. There are 2 oxygens. So if each oxygen gained 2 electrons, and there are 2 oxygens, then really 4 electrons total were gained throughout the course of this reaction. Now if I look at this, my oxidation half reaction shows 8 electrons being lost, but my reduction half reaction shows 4 electrons being gained. And that doesn't work out. So how could we fix that problem? Well, if we double this reduction half equation, then that would give me 8 electrons being gained instead of just 4. That also tells me that I'm going to have to double the amount of oxygen in this chemical equation. And I'm going to have 2 times 2. I'm going to have a total of 4 oxygens on the product side. So to do that, I need to double the amount of water. And that actually helps me balance this equation. Now this equation is balanced. Okay, so for example 3, we have one single compound reacting to form 2 separate products. And so any reaction in which you start with one single reactant, that's going to be a decomposition reaction. And we're going to go ahead and assign oxidation numbers to each element in this reaction. So we have a couple that we have rules for. Oxygen, again, is an element over here, and so since it's a pure element, it's going to have an oxidation number of 0. I see potassium, an alkali metal, and it's going to carry a charge of positive 1 everywhere it is. I see oxygen in a compound. Again, that's going to carry the oxidation number of negative 2. And then I see chlorine, a halogen, in this compound, and that's going to carry an oxidation number of -1. But chlorine as a reactant is not going to carry an oxidation number of -1 here, because I recognize the polyatomic ion chlorate. And so since this chlorine is actually part of a polyatomic ion, it was one of our rules. It's one of the exceptions, actually, to the rule that halogens do not have an oxidation number of -1 if they're part of a polyatomic ion. So since this chlorine is part of the chlorate polyatomic ion, it's not going to be -1. Here it wasn't part of a polyatomic ion, it was just the anion in this ionic compound. But here it's actually part of a bigger anion. And so we need to figure out what the oxidation number of this chlorine is going to be right here. And so again, we just do a little bit of math to figure this one out. I know that chlorate, the polyatomic ion, carries a charge overall of -1. So the sum on chlorate is going to be -1. I also know that each oxygen carries an oxidation number of -2, and there are 3 of them, and so that's a net of -6. So what can we add to -6 to end up with just -1? Again, that's going to be +5. So +5 minus 6 is -1. If I put a +5 right here on this compound, the sum on potassium chlorate is 0, and the sum on the chlorate ion is -1, which cancels out the +1 from the potassium. So these should be the correct oxidation numbers for each element in this compound. We need to again look at it and figure out what was oxidized and what was reduced, what changed. Now potassium was the same on both sides, but I do see that both chlorine and oxygen changed from the reactant side to the product side. So if I look at oxygen, it went from -2 to 0. So again, on my number line, if I'm moving from -2 to 0, I'm moving in a positive direction, and so oxygen was oxidized. Chlorine went from +5 to -1, so it obviously became more negative in charge, which means that it was reduced. And now we need to write the half reactions. So for oxidation, we have this oxygen with a -2 oxidation number becoming oxygen, and it's a diatomic element, so we need to keep it a diatomic element here. And that means I'm going to need 2 oxygens to go through this process. Each oxygen is going from -2 to 0, and that's a change of 2 electrons. If I have 2 oxygens, each losing 2 electrons, that's 2 times 2, that's going to be 4 electrons total being lost. And again, I'm not subtracting that, I'm adding it to the product side. So in your oxidation half reaction, you should see the number of electrons being lost added as a product. Similarly, we had chlorine over here. Chlorine had a +5 oxidation number as a reactant, but chlorine had a -1 oxidation number as a product. That's a difference if I use my number line and think about the difference there. I'm going from +5 over here, 1, 2, 3, 4, 5, 6 spaces. So it's actually gaining 6 electrons. So I'm going to add those 6 electrons to the reactant side. So those 6 electrons hook up with this positive chlorine and drop its oxidation number down to -1. Now, here we have an issue because we have 4 electrons being lost and 6 electrons being gained. 4 and 6 are not the same number, and we have to have the same number of electrons being lost and gained. So the lowest common multiple of 4 and 6 is going to be 12. If I take this oxidation half reaction and multiply it by 3, 3 times 4 electrons gives me 12 electrons being lost. If I take my reduction half equation and multiply it by 2, 6 times 2 electrons is 12, and now I have 12 electrons being gained. So if I figure out what to multiply these by in order to get the same number of electrons in both equations, that actually helps me figure out what my coefficients are going to be. I'm going to need 3 O2s in this equation, and I need 3 times 2 oxygens on this side. I need 6 oxygens on this side, so 3 times 2 gives me 6 oxygens on the reactant side as well. That also tells me that I'm going to have to double chlorine, which we already did right here. We just doubled chlorine by putting that 2 there, but we need to go ahead and double it on the product side as well. So figuring out how we're going to multiply these in order to get the same number of electrons being gained and lost helps us figure out what these coefficients are going to be as well. That also tells me that 3 times 4, 12 electrons were transferred. So 12 electrons were lost by the oxygens, and then those same 12 electrons were picked up by the chlorines. So 12 electrons were transferred between those two elements. And for our last example, we have elemental magnesium, so again, oxidation number 0, and elemental oxygen, oxidation number 0, combining to form the product magnesium oxide. Oxygen is -2, and to cancel that out, and because it's an alkaline earth metal, magnesium is +2. So we went ahead and assigned those oxidation numbers. I can also think about the fact that I have two reactants combining to form a single product, and that indicates to me that this is a synthesis reaction. So now we need to look at it and think about what element was oxidized and what element was reduced, and we really don't have too many options here. I see that magnesium went from 0 to +2. So again, if it went from 0 to +2, it moved in a positive direction on the number line, it was oxidized. So magnesium was oxidized, which means that oxygen had to be reduced because we don't have any other options there. For the oxidation half reaction, we have magnesium becoming a magnesium ion with a +2 charge. In the process, it loses 2 electrons. So those 2 electrons are going to be represented on the product side of my oxidation half reaction. Then I see oxygen again as a diatomic, so I know that I'm going to need 2 of them on the product side anyway, so let me just go ahead and put it there. And on the product side, they're going to have that oxidation number of -2. So again, I have 2 oxygens. Each oxygen is gaining 2 electrons. So 2 oxygens times 2 electrons is going to be 4 electrons gained. And that's going to be my reduction half reaction. Now, one issue with this, again, we have 2 electrons being lost, but 4 electrons being gained, and that's impossible due to the law of conservation of matter. So we need 4 electrons to be lost if 4 electrons are going to be gained. And I know that if we double this half reaction right here, that's actually going to do the trick. And so what that tells me is that I need to have 2 magnesiums present on each side of this chemical equation, and that goes ahead and balances it out. It also tells me that I have 2 times 2, 4 electrons being lost here, 4 electrons being gained here. I have 4 electrons being transferred between magnesium and oxygen. So I hope going through these examples helps you guys understand how to assign oxidation numbers, how to determine what was oxidized and what was reduced, and also how to write oxidation and reduction half reactions and use them to help you balance redox equations.